Okay, so Blake, before watching this, make sure you've watched the crash course video on cellular respiration. The link should be in the email. Okay, so to review, so if you look at your book on page 477 and then on page 478, you've got a pair of, one is a table and one is a figure. That table is a big part of what I'm rolling into this chart, as well as kind of simplifying the figure that's on 478. If you know this and can explain what it means by the end of studying, then you should be good for a really big portion of the test. It's not enough to just be able to create this from memory, you need to understand it. So if you guys want, I can also send you this video too if you want to be able to review. So our first step, these are the steps of cellular respiration. So we talked about external respiration, which is what happens in our lungs to get the air from, or the oxygen, from the external air into our bodies. Then the next step in respiration in general is transport in our circulatory system, moving the oxygen in your blood to the tissues. Then we have internal respiration, which moves it from your blood into the actual cells. But now we've got oxygen there, and we've got to figure out what to do with it, right? So what we do with it is cellular respiration, this process. So we start with glucose. Glycolysis very literally means glucose breaking, right? So that's that first step. So glucose.
Separating or breaking.
Yeah, separating or breaking. Lysis means to break. Glucose breaking. In this step, what we need to do it, there are a whole lot of other things. He talked about like a cast of finger puppets with all the enzymes and stuff. We don't care about that level. That's like late college. You don't care about that right now. Right now, we're just looking at kind of the simple overall. So in the most simple sense, we need glucose, because that's what we're breaking, right? We need to spend a couple of ATP for the energy to do the breaking, and we need a couple of NAD+ molecules that are already hanging out in your cell. By the magic of modern television, these things get worked on by all those enzymes, and what kicks out is 4 ATP. So we put 2 in, we get 4 out. That's a net gain of 2, right? We're up by 2. We get 2 NADH+ molecules. I put them in purple because I want you to see they're going to come down here to the last step. And that's what this dotted line is. And then we also get 2 pyruvate molecules. So these are what come out of glycolysis. I've put glycolysis in blue here to remind you that you don't need oxygen for it. This is an anaerobic process. So when you're exercising really, really hard, remember when we watched the Julie Moss video where she was doing the Ironman triathlon and she just like completely ran out of energy. She had done as much glycolysis as she could do, and she was completely out of glucose at that point, right? She would have been more productive in a sense, if she hadn't been exercising, had more oxygen happening and could get down into the aerobic steps, but that's kind of the nature of the beast with exercise. So, first step, glycolysis doesn't require oxygen. You see we don't need oxygen here, right? And we get out our pyruvate. So then we move to step 2. Move this up. Oxidization of pyruvate. And he didn't call this a whole separate step in the video, you might have noticed. So oxidization means add, what do you think?
Oxygen.
Add oxygen, very good, add O2. So we're adding oxygen to these pyruvate molecules. We got the pyruvate from our first step. We needed to also add some oxygen, like we said, and some NAD, or NAD+, I mean. Again. And what we get out of this step, all you need to know is we're cutting off some carbons and combining them with those oxygens, which is why we get carbon dioxide. So now this is where we start to build up some carbon dioxide waste that we need to get rid of by exhaling, right? That's where it comes from. The first part of it is from this step. We also get some NAD+, because we've added some hydrogen ions onto these, and we'll use those later. And then we also get this acetyl-CoA. The acetyl-CoA is part of that Krebs cycle. In your book, there's actually like a circle that they show. It involves citric acid, it involves oxaloacetic acid. You don't have to know the ins and outs of how that happens. Just know it's called the citric acid cycle, and that it uses these acetyl-CoA molecules. We're also, again, adding some NAD+. So you can see we use this all the time, right? We're adding these FAD molecules as well. And then we're going to need some more oxygen. So again, we're in aerobic respiration. And we need a little bit of ADP to load up and turn into ATP, right? What we get out is some more carbon dioxide waste to get rid of. We get a couple more ATP. That's what happened with these ADPs. And then we get some NAD+ and FADH2 molecules. And like he talked about, all these NADH molecules and FADH2 molecules, they're all like batteries. It's basically like loading something up with some energy that we're going to use now in this last step to load into our ATP. So we take all those battery molecules that are holding like this potential energy ready to go, and we do that electron transport chain that he had that nice little animation. So the electrons break off, and they take a hydrogen ion, which is a proton, with them. The electron pushes the hydrogen out of the cell, and then the hydrogen wants to come back in. And as it comes back through the ATP synthase, that molecule that they showed on the far right side of the picture, as it comes back in, it's powering that ATP synthase molecule to start sticking ADPs and ATPs, or ADPs and phosphate molecules together. So it's basically just taking that energy from here and using it to lock ADP and phosphates together to make this molecule. Make sense?
Yeah.
So just to review, doesn't need oxygen. These ones do need oxygen. In each one, this is what's going in. This is what's coming out. And I've tried to kind of color coordinate things so that you can see as your outs contribute to their next step. That's what the green is. And then all of these NADH and the FADH2 molecules come together at the end. They've been collected all the way through to come together at the end to be used in the electron transport chain to power getting out. Now we're back to FAD molecules, NADH plus molecule, or NAD plus molecules, right? So, which we're going to use up here again. They get reused. We get some water out of the whole process, and we get 32 ATP from this one step. So if you look, we actually can get 4 ATP plus 2 ATP is 6, right? So we can get a total of 38. If we subtract these 2 that we had to use to even start things, then it's like 36. And like he did mention, that's really best case scenario. That's not every cell is kicking out quite that efficiently, but that's what they can do. I can't remember how many he might have said 38. There's some debate from one text or resource to the next about exactly how many you get, but 36 to 38 is kind of the agreed upon range for ideal situations.
Can I take a picture?
Yeah, absolutely. So, we're actually done with that kind of early. Didn't take all that long. I really do recommend that you read the section about cellular respiration and watch that video a couple more times, just till it doesn't seem like so...
Mumbo jumbo.
Yeah, exactly. When it starts to seem a little more real and makes sense, then you're probably approaching where you need to be. Are there any places in this chapter, take a second and look through it and tell me if there's anything you need me to go over, anything that didn't make sense so far. Blake, I'm going to go ahead and turn you off.